Everyone. So today we're going to go over some worksheet problems. All right, so worksheet problem 2. Remember last time we saw that some radioactive elements can go through a series of decays. So we might have multiple alpha decay steps or a few beta decay steps, but eventually what ends up happening is we see a stable isotope at the end. So let's write a partial decay series for radon 220. And we're already told that it starts with an alpha decay, followed by another alpha decay, and then a beta decay, and then another beta decay. Now this is just a partial series, it's not the full decay series, so the isotope we end up with here might still be radioactive. Okay, so let's start with the first decay, which is alpha decay. So I'm just rewriting radon 220, and if we look up its atomic number, it's 86. All right, so we're already told that this is going to emit an alpha particle, so that's a helium nucleus, which has a mass of 4 and an atomic number of 2, or 2 protons. And then we're going to figure out the daughter nuclide. So the mass number on the left, remember, has to equal the sum of the mass numbers on the right. And same for the atomic numbers. So let's write a simple algebraic expression where 220 is equal to x plus 4. And then we're going to rearrange that to solve for x. So 220 minus 4 is 216. And then let's do the same for the atomic number. What is the new atomic number? So 86 is equal to x plus 2. So if we rearrange that and solve for x, we have 86 minus 2, which is 84. Okay, so let's look up what the element is that has 84 protons. So radon has an atomic number of 86. It's in the noble gases towards the bottom there. So if we look over to the left at atomic number 84, that corresponds to polonium. So polonium has the symbol PO. And this was the radioactive element that Marie Curie named after her home country of Poland. Okay, so that would be PO. All right, so now for the next step in this sequence, we have another alpha decay. So we're going to start with the daughter nuclide from the previous step. So let's rewrite polonium 216. And again, we have another alpha decay. So let's figure out what our daughter nuclide is. So 216 is equal to x plus 4. And if we rearrange, x is equal to 216 minus 4. So that would be 212. So that's our new mass number. So now let's figure out our new atomic number. So 84 is equal to x plus 2. So if we rearrange, x is equal to 82. Okay, so let's look up which element has 82 protons. Okay, so it looks like that's lead, which has the symbol Pb. Okay. All right, so now that's what we'll use in our next step. Now in this next step, now we're going to see beta decay. So remember, beta particles are the same as electrons. So we'll write the symbol for an electron there. You could also put a beta symbol in place of the E. That's okay too. All right, so the mass number will be super easy to solve for because it's just staying the same. Electrons don't have mass, so when we lose an electron, the mass stays the same. The atomic number will change though, so let's solve for that. So 82 is equal to x minus 1. So if we solve for x, that should equal 82 plus 1, which is 83. So let's look up which element is number 83. So that's right in between lead and polonium. So it's bismuth, Bi. Bismuth is actually what's in Pepto-Bismol, but they use a stable version of bismuth. They don't use a radioactive version of bismuth, so nothing to worry about there if you use Pepto-Bismol. All right, so now number 4. We're going to take our bismuth isotope, and our last step is also beta decay. So let's figure out what the daughter nuclide is. Now again, the mass will stay the same, but we have to figure out the new atomic number. 83 is equal to x minus 1. So if we rearrange, x will equal 84. And we already saw previously that the element with atomic number 84 is polonium. So this is really cool. We went from radon to an isotope of polonium, to an isotope of lead, to an isotope of bismuth, and finally we went back to polonium, except this time polonium has a mass of 212. So remember in beta decay that we're turning a neutron into a proton. So that's why the atomic number increases. And that makes sense because what's happening is a neutron is emitting an electron or a negative charge, so it becomes positively charged. And neutrons have very similar masses to protons, so the neutron becomes a proton. So this is really cool. Now for the next worksheet problem, problem 3, we're asked to fill in the missing particles in each nuclear equation. All right. So what's kind of nice here is that everything's already written out for us, so we don't have to go necessarily looking as much stuff up. So we might just have to look up a couple of elements instead of all of the elements. All right, so in A, let's see, the AM stands for, let's see if I can pronounce this, Americium? Americium? I think it's named after America, and then they changed the name slightly. All right, and then we're producing NP, Neptunium. So that's named after Neptune. So again, we want to make sure that the mass numbers add up to the same thing on both sides. And we also want to make sure the atomic numbers add up on both sides. So let's look at the mass numbers. We have 241, on the left, and that's going to equal 237 plus whatever our decay particle is. So let's rearrange. So this will be 241 minus 237, which is equal to our new mass number. So that's a difference of 4. So you might already be able to tell what this is because there's only one particle with a mass number of 4. Now let's figure out the atomic number. So 95 is on the left, and that's going to equal 93 plus our unknown atomic number. So 95 minus 93 is equal to 2. So which particle does that correspond to? An alpha particle. So we could write alpha or helium. Either one is fine. I tend to write helium, but both are correct. All right, so now for B, we're trying to figure out what the parent nuclide is. So we're given the daughter nuclide and the fact that the parent nuclide is releasing an electron, or it's going through beta decay. Okay, so our unknown parent mass is equal to 233 plus 0. So it's just 233. All right, and then the atomic number is equal to 92 minus 1. So that is 91. Okay, so now we do have to look up which element this is. So let's go to our periodic table and figure out which element has 91 protons. Okay, so it looks like this will be in either the lanthanides or the actinides, and it's in the actinides, so the very, very bottom row. So if we look at actinium, thorium, element 91 is right next to that, which is protactinium, or Pa. Protactinium, what a name. Okay, now for part C, we're trying to figure out what the daughter nuclide is. So we've done this quite a bit now. So we're starting with neptunium, and we're seeing some alpha decay here. So on the left, for the mass number, we have 237, and that will equal our unknown mass number plus 4. So if we rearrange, 237 minus 4 is equal to 233. Okay, now let's solve for the atomic number. All right, so 93 is on the left, and that will equal x plus 2. So if we rearrange, x is equal to 93 minus 2, which is 91. Okay, so we already looked this up on the periodic table. It's protactinium. Okay, so that's kind of cool. So neptunium 237 can give us protactinium 233 through alpha decay. And then we can see that protactinium can go through beta decay to produce uranium 233. So that's pretty cool. All right, now the last one. We have bromine. So this is an element we all recognize, hopefully. All right, so bromine 75, and it's going through beta decay, and we're trying to determine its daughter nuclide. So the mass number for the daughter nuclide That's super easy. It will be the same because the beta particle doesn't have any mass. And then we have to figure out the atomic number. So 35 is equal to x minus 1. So if we rearrange that, we have 35 plus 1. So that's equal to 36. And remember, during beta decay, a neutron becomes a proton. So that makes sense. We're seeing an increase in the number of protons. All right, so now let's figure out which element is element 36. So it should be right next to bromine. So that should be krypton, Kr. Okay, so not too bad. Just filling in the blanks, doing some simple addition and subtraction. Now let's move on to worksheet problem 4. So we're going to determine whether or not each nuclide is likely to be stable, and then we want to state our reasons. So this has to do with our last lecture. Remember, we went over the valley of stability, and we talked about how for the first 20 elements, the neutron to proton ratio should be about 1 in order for the isotope to be stable. And then for elements 20 to 40, that ratio should be about 1.25. And then for elements 40 to 80, that should be about 1.5. And then for anything with more than 83 protons, that is unstable. Okay, so we also talked about how if the neutron to proton ratio is too high, then a neutron will try to turn into a proton to kind of even out that ratio. And so that would be through beta decay. And then if the neutron to proton ratio is too low, we'll likely see positron emission or electron capture. So a proton will turn into a neutron. All right, so really what we're looking at is that neutron to proton ratio. So let's start with A. We have titanium 48. All right, so I'm going to rewrite the isotope expression here. And I already looked up the atomic number of titanium. So it is 22. And let's calculate how many neutrons this isotope of titanium has. So we're going to take the mass number and subtract the atomic number. So 48 minus 22 gives us 26 neutrons. Okay. So now we can look at that N over Z ratio. So it's 26 over 22. So the number of neutrons over the number of protons. And this will be about 1.2. Okay, and remember, we just said that for elements 20 to 40, the stable neutron to proton ratio approaches 1.25. So 1.2 really isn't that far off. Now we could also compare the mass number of this isotope to the average mass of titanium. So the mass number is 48, and then the atomic mass number for a bunch of titanium atoms is 47.87. So 48 is really close to that. So I'm inclined to say that this is a stable nuclide because the mass number is very similar to the average mass of titanium. And the ratio of neutrons to protons is pretty close to what we would want for a stable nuclide. Okay, so my conclusion there is that it is stable. So let's move on to chromium 63, and I'll use a different color here. So I looked up chromium's atomic number. It is number 24. So let's figure out the number of neutrons. So 63 minus 24. So that should give us 39 neutrons. Okay. So let's look at the neutron to proton ratio. So that's 39 over 24. And that gives us 1.6. That seems a little high. So actually, let's look. So again, for elements 20 through 40, a stable neutron to proton ratio is about 1.25. So 1.6 is quite high. So I'm going to say that there are too many neutrons, but let's compare the mass of this isotope to the average mass for chromium. So the average mass is 52. So 63 is way higher than 52. So I'm going to say this is unstable. Most likely, one of the neutrons would try to become a proton, or we would see alpha emission. So this would be unstable. Okay, so I'm going to ask you to try C and D on your own, and you can always consult the worksheet key if you get stuck. All right, so in the next lecture, we'll talk more about how to detect radioactivity, so different methods for that. And then we'll also go on to talk about some uses of radioactivity. So how is it actually helpful? So I will see you in the next video.